A photon now reaching Earth began traveling before our planet existed. This is the ancient light we will trace, the universe's earliest signal. By the end, you will see the definitive portrait of our cosmic beginnings and understand where everything came from. We are going to decode whispers from a time when stars and galaxies had not yet formed, uncovering what these fading echoes reveal about our own origins. How does it feel to look directly into the dawn of everything? To find that first light, we must return to the very beginning, to a moment of such profound density and heat that our familiar ideas of space and time simply fall away. Think of it not as an explosion in an empty void, but as the rapid, everywhere at once expansion of space itself, filled with a searing and opaque plasma. For nearly 400,000 years, the infant universe was a churning and brilliant fog. Light existed, but it was imprisoned. A photon could travel only a minuscule distance before meeting a free electron, bouncing and scattering in a frantic and trapped dance. This era is often called the Cosmic Dark Ages, a profound misnomer, for it was a universe ablaze with energy yet completely blind to itself. Nothing could see through that glowing and impenetrable soup. Then a great cooling happened. As the universe expanded, it stretched and diluted that primordial energy. The temperature dropped from millions of degrees to a few thousand, a change that triggered one of the most important events in cosmic history, an event we call recombination. It is a quiet and technical term for a cosmic revolution. When the universe cooled enough, electrons finally slowed down and were captured by protons, forming the first stable atoms, mostly hydrogen. In that instant, the prison bars vanished. The free electrons that had been scattering light were suddenly bound inside atoms. For the very first time, photons could travel unimpeded. The universe, in a flash, became transparent. That first burst of liberated light, rushing outward in every direction, is what we call the cosmic microwave background. It is not a flash from a single point, but the release of the glow that had filled the entire cosmos, suddenly set free to travel across the ages. This is the oldest fossil in existence, a snapshot of the universe taken when it was a mere 380,000 years old. Every direction we look, this faint and cold whisper of microwaves washes over us, a direct signal from the dawn of time. Its discovery, an accidental finding by two radio astronomers puzzled by a persistent hum in their antenna, would become the single most important piece of evidence for our modern story of the beginning, transforming cosmology from speculation into a precise science. But how do you hear a whisper from the edge of time itself? How did we learn to read the secrets held within that ancient light? That persistent hum was the sound of the universe introducing itself. Arno Penzias and Robert Wilson, two radio astronomers working at Bell Labs in the mid-1960s, were not looking for the dawn of time. They were simply trying to calibrate a sensitive new horn antenna, a massive device designed for satellite communication. Their goal was to measure faint radio signals from space, but their work was constantly met with an unshakable, omnipresent static. It was a low, steady hiss that came from every direction, day and night, and it would not go away. They assumed it was local interference, perhaps from nearby New York City. They checked their equipment, tightened every connection, and pointed the antenna in every conceivable direction. The hum remained. They even considered a more mundane source, pigeons. The birds had been roosting inside the large horn, leaving behind a residue. They cleaned it out meticulously, even encouraging the pigeons to find a new home, but the mysterious noise persisted. This was not a glitch, it was a signal, and it was coming from the sky itself. Their curiosity about this unshakable noise was about to meet a separate line of theoretical work. At nearby Princeton University, a team led by Robert Dick was actively searching for this very signal, a predicted cooled remnant of the universe's hot beginning. When Penzias and Wilson, baffled, reached out to them, the pieces snapped together with breathtaking clarity. That inescapable static was not a defect, it was a detection. It was the cosmic microwave background, the cooled and stretched afterglow of the universe's initial fireball, bathing the entire Earth. The discovery was monumental. It transformed cosmology from a field of elegant speculation into a rigorous observational science, for providing the first tangible, physical evidence of the universe's explosive origin. Penzias and Wilson received the Nobel Prize in Physics in 1978. Their story is a powerful reminder that the universe often speaks in whispers, and sometimes the most profound truths are found not in what we seek, but in what we cannot seem to silence. This noise was the oldest song in existence, and we had finally learned to hear it, but a uniform hum, while revolutionary, only tells part of the story. If the early universe was perfectly smooth, how did we get here? That uniform hum was only the beginning of the story. The true revelation came when we learned to see the intricate patterns hidden within it. The cosmic microwave background is far more than a smooth, ancient glow. It is a detailed fossil, a snapshot of the universe at 380,000 years old, imprinted with the faintest of wrinkles. These are not flaws, but the most important features of the entire image. We call these minute variations anisotropies, tiny differences in temperature from one patch of the sky to another. To our most sensitive instruments, this so-called uniform bath resolves into a spectacular map, a mottled tapestry of warmer and cooler spots. This map is often called the universe's baby picture. Like a baby's features hinting at the adult to come, these spots tell us everything about our cosmic destiny. What do these temperature differences mean? They are direct imprints of the very first structures in existence. Think of the early universe as a vast sea of hot plasma, not perfectly smooth, but with incredibly subtle ripples. In regions where the plasma was ever so slightly denser, gravity had a stronger grip. These overdense regions appear to us as slightly cooler spots in the microwave background. Conversely, the slightly emptier, underdense regions appear as warmer spots. This difference is almost unbelievably small, varying by only about 1 part in 100,000. You could compare it to looking at a vast, smooth desert and detecting sand dunes only a few millimeters high. Yet these minute imperfections were the seeds of everything. Those slightly denser, cooler patches were gravitational wells, the primordial gathering places where dark matter and normal matter would slowly, over hundreds of millions of years, begin to pool. From these tiny seeds grew the vast cosmic web, the filaments and voids, the clusters of galaxies, the stars, and the planets. Every structure you see in the night sky, and indeed every atom in your body, can trace its lineage back to one of these specific wrinkles in the ancient light. Reading this fossil required a new generation of eyes. Ground-based observations could only hint at these variations. To see them clearly, we had to go above Earth's atmosphere. This began with NASA's a Cosmic Background Explorer satellite in the early 1990s. It did not just confirm the background radiation. It made the first blurry map of its anisotropies, proving the variations were real. It was like putting on a pair of glasses for the first time and seeing the individual leaves on a distant tree. The mission was followed by the Wilkinson Microwave Anisotropy Probe, which delivered a far sharper image. This detailed full sky map allowed scientists to measure the universe's age, composition, and geometry with unprecedented precision. Finally, the European Space Agency's Planck satellite, with even greater sensitivity, provided the most exquisite portrait we have. It is a map of such fine detail it feels like we are staring directly into the quantum fluctuations that seeded the cosmos. These missions translated a nearly uniform microwave bath into a rich cosmological ledger. By analyzing the size and distribution of these hot and cold spots, scientists could read the story written at the beginning of time. They could measure how much ordinary matter, dark matter, and dark energy the universe contains. They could confirm the geometry of space is flat. They could even discern hints of the universe's very first split second of expansion, a period called inflation. This ancient light is not just a relic, it is a Rosetta Stone, and we have finally learned its language. But if this light shows us the seeds, what planted them in the first place? What force could have created those first, crucial imperfections in the smooth fabric of the newborn cosmos? That detailed map of hot and cold spots is more than a picture, it is a precise cosmic blueprint. Each subtle variation in temperature is a data point, a whisper from the infant universe that tells us exactly how it was built. The overwhelming uniformity of the background, the fact it looks almost the same in every direction, confirms a profound truth on the largest scales: the universe is isotropic. There is no special center, no preferred direction. It is homogeneous and even. This large-scale smoothness is the direct result of the universe's explosive initial growth spurt, a period called inflation, which stretched any primordial irregularities to near invisibility. Yet those tiny remaining wrinkles, the anisotropies, are where the real information is stored. They are not random noise, they follow a specific and predictable statistical pattern. Cosmologists analyze this pattern like a musician reading a complex musical score. The size and distribution of the hot and cold spots reveal the fundamental properties of our cosmos with astonishing accuracy. Think of the spots as sound waves frozen in time, echoes of pressure waves that rippled through the early plasma. The most common size of these spots acts as a standard ruler. By measuring its angular size on the sky and knowing how far the light has traveled, we can calculate the geometry of the universe itself. The result is definitive: space is flat. Not flat like a sheet of paper, but flat in the geometric sense that parallel lines remain parallel, and the angles of a triangle add up to exactly 180 degrees. This flatness tells us the total density of the universe is precisely balanced, a critical clue about its composition and ultimate fate. From this blueprint, we can read the universe's ingredient list. The precise way matter and radiation interacted in those first sound waves left a distinct signature in the spot pattern. By decoding it, scientists have determined the cosmos is made of about 5% ordinary matter, the atoms that form stars, planets, and us. Roughly 27% is dark matter, the invisible gravitational glue that holds galaxies together, and a dominant 68% is dark energy, the mysterious force causing the expansion of the universe to accelerate. We even know its age, 13.8 billion years, a number pinned down by measuring how long it took for those sound waves to travel and for the light to finally reach us. This makes the cosmic microwave background the ultimate calibration tool, a cosmic ruler and scale against which all other measurements are checked. It is a direct readout of the universe's initial conditions, the settings that were in place when structure first began to form. Every galaxy cluster, every spinning spiral, every planet orbiting a distant star was constructed from the blueprint imprinted in that ancient light. But such a perfectly tuned setup invites an even deeper question. What kind of physics, operating in the universe's first incomprehensibly fleeting moment, could have established these conditions with such exquisite precision? The blueprint we can read so clearly today required a cosmic artist of unimaginable power. To find the source of those first wrinkles, we must rewind the clock not just to hundreds of thousands of years after the beginning, but to a time so brief it defies comprehension, a fleeting moment known as the Inflationary Epoch. The universe we see is vast, smooth, and geometrically flat, conditions that the standard Big Bang model struggles to explain on its own. How did regions of space now billions of light-years apart, which could never have been in contact, come to share the exact same temperature and properties. The elegant and mind-bending answer is inflation. In the first sliver of a second after the beginning, the universe is thought to have undergone a period of hyper-accelerated, exponential expansion. Space itself stretched faster than the speed of light, inflating a subatomic volume of primordial chaos to a size larger than our entire observable cosmos in less time than it takes light to cross a single proton. This incredible event did two critical things. First, it took any pre-existing irregularities and stretched them so dramatically that the cosmos became incredibly smooth and uniform on large scales, explaining the remarkable isotropy of the cosmic microwave background. Second, and most importantly, it acted as a cosmic amplifier for the tiniest of seeds. Even in that initial state, the universe was not perfectly quiet. At the quantum level, there is always a faint jitter, a seething foam of virtual particles popping in and out of existence. Inflation, as it stretched the fabric of space-time, took these microscopic quantum fluctuations and blew them up to macroscopic size. Imagine the faintest ripple on a pond suddenly being stretched into an ocean-wide wave. These amplified quantum jitters became the primordial density variations, the slight over-densities and under-densities that gravity would later use as construction sites. This is the direct link between the unfathomably small world of quantum mechanics and the vast architecture of the cosmos. Those quantum whispers, stretched across the entire sky, became the pattern of warmer and cooler spots we see imprinted on the cosmic microwave background. The evidence for this theory is written in that ancient light. The specific statistical signature of the hot and cold spots, their distribution and size, matches the predictions of inflationary models with stunning accuracy. Furthermore, inflation naturally predicts a flat universe, which is exactly what the detailed measurements of the cosmic microwave background have confirmed. While we cannot directly observe the inflationary epoch itself, its fingerprints are all over the universe's first photograph. It is the crucial chapter that explains not just the smoothness, but the very origin of the seeds that grew into galaxies, stars, and us. It transforms the cosmic microwave background from a simple snapshot into a detailed record of the universe's first and most dramatic growth spurt, a moment when the quantum realm wrote the destiny of the cosmos. But if inflation set the stage, what was the universe like in the fiery moments that immediately followed? What filled that newly stretched space before the first atoms ever formed? The quantum ripples stretched by inflation did not remain silent. They began to ring. In the first few 100,000 years, the universe was not a quiet void but a seething, dense fluid, a tightly coupled mix of ordinary matter, dark matter, and intense radiation. This primordial soup was a perfect medium for sound, but sound of an almost unimaginable scale. Pressure waves driven by gravity and radiation began to propagate through the hot plasma. Think of dropping a stone into a still pond, sending circular ripples outward. Now imagine that stone is a region of slightly higher density, and the pond is the entire observable universe. These were the first symphonies of structure, colossal sound waves moving at a significant fraction of the speed of light. We call their fossilized imprint Baryon acoustic oscillations. For nearly 400,000 years, these pressure waves surged outward from every overdense seed. Ordinary matter, the baryons, wanted to collapse inward under gravity, but it was trapped in a fierce tug-of-war. The intense radiation pressure of the early universe acted like a powerful spring, pushing the matter back outward. This created a rhythmic oscillation, an in and out sloshing of the plasma. The waves traveled until the moment of recombination, when the universe cooled enough for atoms to form. In that instant, the music stopped. The radiation, now decoupled from matter, streamed away as the cosmic microwave background. The matter, suddenly freed from the radiation's pressure, was frozen in place. Each wave was caught mid-oscillation, leaving a lasting pattern, a spherical shell of matter with a slight over-density at a very specific distance from the original seed. This creates a subtle but detectable signature. In the detailed maps of the cosmic microwave background, we see a preferred scale for the hot and cold spots, a characteristic size imprinted by the distance those sound waves could travel before the universe became transparent. More strikingly, this same scale is stamped onto the large-scale structure of the universe we see today. When astronomers map the positions of millions of galaxies, they find a faint but statistically significant tendency for galaxies to be separated by a specific distance, about 500 million light-years. It is as if the universe is dotted with faint, ghostly rings, all the same size, the preserved echoes of those first cosmic sound waves. This distance is our standard ruler. Because we know the physical size of this acoustic ruler from the physics of the early universe, we can use it to measure cosmic distances with extraordinary precision. By observing how the apparent size of this ruler changes at different epochs, looking back to the cosmic microwave background and forward to galaxy surveys of the nearby universe, we can trace the expansion history of the cosmos across billions of years. It acts like a series of mile markers along the highway of time. This independent measurement provided one of the most robust confirmations of dark energy. The data showed that the expansion of the universe began to accelerate about 5 billion years ago, stretching that standard ruler in a way that only a repulsive force like dark energy could explain. These preserved sound waves, a direct product of the universe's first dynamic moments, have become one of our most reliable tools for understanding its entire life story. But to hear the very first note of that symphony, we must listen for something even fainter, a polarization in the ancient light that hints at the universe's dramatic birth. The ancient light holds a hidden diary, written not just in temperature but in the very direction of its vibrations. This property, called polarization, is a whisper within a whisper, a subtle pattern in how the light waves oscillate. As the cosmic microwave background radiation finally streamed free at recombination, it was imprinted with a specific kind of order, a fossilized record of the last interactions it had with the hot plasma of the early universe. To understand it, think of light as a wave rippling through space. Normally, these waves can vibrate in any direction perpendicular to their travel. Polarization is when those vibrations are given a preferred orientation, like ocean waves rolling in parallel lines toward a shore. The cosmic microwave background carries two distinct types of this hidden pattern, known as E modes and B modes. E modes are the simpler story, a direct echo of the density fluctuations we already see in the temperature map. They were created by the scattering of light off the clumps of electrons in those last moments before the universe became transparent. The pattern of these E-mode polarizations looks like radial patterns or curls emanating from the hot and cold spots on the sky. They provide a powerful cross-check on the standard model of cosmology, confirming the physics of that pivotal moment of recombination with even greater precision. But it is the second type, the B modes, that sends a thrill through the cosmology community. These are a different kind of swirl, a curling pattern in the polarization that cannot be created by simple density variations. Their most exciting potential source is something far more dramatic: primordial gravitational waves. These would not be waves in water or air, but ripples in the very fabric of space-time itself, theorized to have been generated during the violent inflationary expansion. If inflation truly happened, the universe's explosive growth should have shaken the foundations of reality, sending powerful tremors through space-time that would have left a unique, curling signature in the polarization of the cosmic microwave background. Detecting these primordial B modes is considered a major goal. It would be our most direct evidence for inflation, a key piece of evidence from the universe's first trillionth of a second. More than that, the strength of the signal would tell us about the energy scale of inflation itself, probing physics at energies 1 billion times higher than any particle collider on Earth could ever reach. It is a chance to listen to the earliest moments of the cosmos. The hunt for this signal is a story of extraordinary ambition and painstaking care. Experiments like BICEP, located at the South Pole to take advantage of the extremely dry and stable atmosphere, scan the sky with exquisitely sensitive telescopes, searching for that faint curling pattern. The challenge is monumental. The signal they seek is incredibly faint, and the universe is full of imposters. The most significant confounding factor is dust within our own Milky Way galaxy. Interstellar dust grains, aligned by magnetic fields, can also polarize light and produce B-mode patterns that look identical to the cosmological signal. Distinguishing the ancient whisper from the local noise is a detective story at the very frontier of science. It requires combining data from multiple experiments across different frequencies, meticulously mapping and subtracting the galactic foreground, a process of cosmic forensics. Each announcement of a potential detection is followed by intense scrutiny and collaboration, as the global community works to separate the story of creation from the material of our own galactic neighborhood. This meticulous search reminds us that the universe's deepest secrets are not given up easily. They are earned through patience, precision, and a relentless dedication to listening. The search for primordial B-modes is a quest to hear the first tremors of space itself. But the story of light in the universe did not end with that ancient microwave glow. After the cosmic background radiation streamed free, the cosmos entered its true dark ages. For millions of years, there were no stars, no galaxies, only a vast and silent sea of cooling hydrogen gas expanding in the darkness. This profound quiet was broken by a new kind of dawn, not of photons from a fireball, but from the first nuclear furnaces igniting in the void. We call this pivotal era the cosmic dawn. It marks the moment when gravity finally won its long struggle, pulling together the densest of those primordial seeds into the very first stars and galaxies. Their birth was a revolution. For the first time since the Big Bang's initial flash, new light pierced the cosmic dark. This new light, however, did something extraordinary. It began to change the universe itself, interacting with the vast ocean of neutral hydrogen that filled all of space. To witness this transformation, astronomers listen for a very specific cosmic note, the 21-centimeter line. This is not light from a star, but a faint radio whisper emitted by the hydrogen atom itself. Inside a neutral hydrogen atom, the proton and electron act like tiny magnets. They can spin in the same direction or in opposite directions. The opposite spin state holds a tiny bit more energy. When the electron spontaneously flips to align with the proton, it must release that minuscule excess energy. It does so by emitting a photon with a wavelength of exactly 21 centimeters. This is a hyper-specific fingerprint of neutral hydrogen. Across the early universe, countless trillions of atoms were emitting this faint signal, creating a subtle radio glow that bathed the cosmos during the Dark Ages and the cosmic dawn. The key to using this signal as a time machine is the expansion of the universe. As this ancient 21-centimeter light travels for billions of years to reach us, space itself stretches, lengthening its wavelength. The more distant the source, the longer the light has traveled, and the more redshifted the signal becomes. A 21-centimeter photon emitted just after the Dark Ages might reach us with a wavelength stretched to several meters. This means that by tuning a radio telescope to different wavelengths, we are effectively tuning to different chapters in cosmic history. We could, in principle, scan through the frequencies and assemble a three-dimensional movie of the universe's adolescence, watching frame by frame as the first structures ignited and changed their surroundings. The plot of this movie is the epoch of reionization. The first stars and galaxies were behemoths, blazing with intense ultraviolet radiation. this fierce light began to strip electrons from the surrounding neutral hydrogen atoms, reionizing the gas and creating vast, growing bubbles of transparent, charged plasma within the neutral sea. By mapping the distribution of the 21-centimeter signal, we could watch these bubbles form, grow, and eventually overlap as the ultraviolet light from the first structures carved out the transparent universe we see today. This signal is older in terms of cosmic history than the starlight from almost any galaxy we can see with optical telescopes. It is a direct probe of the universe's most formative and dramatic transition since its birth. Capturing this faint echo from the dawn of structure is the goal of a new generation of instruments, most notably the upcoming Square Kilometre array. This colossal observatory, with thousands of antennas spread across South Africa and Australia, is being built to have the sheer sensitivity to detect this incredibly redshifted whisper. Its mission is to produce the first maps of the cosmic web during reionization, revealing the locations of the very first stellar nurseries and tracing how their influence spread. It is an attempt to turn a silent, dark chapter of cosmic history into a vivid narrative, watching as the first points of light began to sculpt the cosmos we now call home. The universe settled into a profound and silent chapter. For nearly 100 million years after the cosmic microwave background streamed free, no new light pierced the vast expanse. This is the true cosmic dark ages, a span longer than the entire history of life on Earth, yet one that left no shining monuments for our telescopes to find. It is the ultimate mystery in cosmic history, an epoch defined by what we cannot see. With no stars, no galaxies, and no new sources of brilliant radiation, the cosmos was an expanding sea of neutral hydrogen gas, cooling and growing darker under the fading echo of its own birth. Observing this era directly seems an impossible task. How do you illuminate a time when the lights were truly off? Yet this apparent silence is deeply deceptive. The Dark Ages were not a period of stillness, but of slow and invisible preparation. Gravity was the quiet architect working without a blueprint. Those tiny wrinkles imprinted on the cosmic microwave background, the subtle overdensities, were its only guide. Across millions of years, the relentless pull of gravity amplified these slight imperfections. Atoms of hydrogen and helium, along with the unseen scaffolding of dark matter, began a glacial drift toward these denser regions. The universe, once nearly smooth, was slowly beginning to gather itself. This is the crucial, hidden transition the Dark Ages hold the secret to, the mysterious bridge between the simple, uniform infant universe and the spectacularly complex cosmos we see today. Understanding this bridge means exploring how nothing becomes something. To pierce this darkness, astronomers must become cosmic listeners, tuning their instruments not to light, but to a specific and ancient hum. Their most promising tool remains the 21-centimeter line, the faint radio signature of neutral hydrogen. During the Dark Ages, before any stars lit up, the entire universe was filled with this gas, all of it emitting that same subtle whisper. The goal is to detect what is called the global 21-centimeter signal, an all-sky radiotone that changes in pitch over time. Think of it as a single, deep note played by the entire cosmos, a note that shifts as the environment changes. Early in this chapter, the gas was still gently warmed by the residual heat of the cosmic microwave background. As the universe expanded, the gas cooled faster than the background radiation, causing the hydrogen to absorb more of this ambient energy than it emitted, which should create a dip in the radio signal we receive. Later, as the first structures began to form and eventually ignite, their radiation would warm the gas again, changing the note once more. By capturing this evolving tone, we could chart the thermal story of the universe through its darkest hours. The experimental challenge is staggering. This signal is incredibly faint, buried under a roar of foreground radio noise from our own galaxy, from Earth's atmosphere, and from human technology. It is like trying to hear a single violin note from an orchestra playing on the other side of the world, while standing in the middle of a bustling city. Projects like the experiment to detect the global epoch of reionization signature use purpose-built, simple radio antennas in remote locations to try and isolate this cosmic murmur. In 2018, one such team reported a tantalizing signal that was far deeper than models predicted, suggesting the early gas may have been cooled by an unexpected interaction. This result, while not yet confirmed and hotly debated, highlights the potential of this approach. Discovering even a single data point from the Dark Ages could reshape our understanding of the universe's formative years. Theoretical models of this era are our guidebooks, sophisticated computer simulations that follow the gravitational dance of dark matter and gas from the seeds in the cosmic microwave background all the way to the emergence of the first celestial structures. These digital universes show halos of dark matter coalescing, with pools of hydrogen gas flowing into their gravitational wells, cooling, and eventually fragmenting into the first generation of stars. These models predict how the global 21-centimeter signal should sound, providing a template for the experiments to match or challenge. Every attempt to listen is a test of our entire cosmic story. Success would give us a direct measurement of the universe's temperature during its long quiet period, and a precise timestamp for when the first stars finally began to shine. This silent era, once thought to be an impenetrable gap in our knowledge, is now the frontier. It holds the answer to how a smooth beginning became our structured home, and to hear its story, we must learn to listen in the dark. These ancient whispers demand extraordinary ears. To capture the universe's faintest signals, we have built specialized observatories that function as true time machines. Each is an engineering marvel, designed to detect specific wavelengths of light that have been stretched and cooled by billions of years of cosmic expansion. The most famous of these time machines are the space-based satellites that gave us our clearest view of the beginning. The European Space Agency's Planck spacecraft, orbiting a distant point in space, was perhaps the ultimate cosmic photographer. Its mission was to map the cosmic microwave background with a sensitivity and precision never before achieved. To do this, its instruments had to be cooled to just a fraction of a degree above absolute zero, minimizing their own heat from interfering with the faint, cold glow of the ancient universe. Planck's final map, released in 2013, is our definitive baby picture. A snapshot of such clarity, it revealed the subtle patterns of the early cosmos in exquisite detail. But not all time machines need to leave Earth. Some of the most powerful are rooted in the most extreme environments on our planet. High in the Chilean Andes, at an altitude of over 5,000 meters, sits the Atacama Cosmology Telescope. This location is chosen with careful purpose. The air here is incredibly thin and dry, as the Atacama Desert is one of the most arid places on Earth. Water vapor in the atmosphere absorbs microwave radiation, creating a blurry veil between the telescope and the pristine signal from the early universe. By placing the telescope in this high-altitude desert, scientists lift it above much of that interfering blanket, giving it a clearer window to the past. Its mission complemented Planck's, focusing on smaller patches of the sky with even finer resolution to study the detailed physics of those primordial sound waves. The next generation of this ground-based work is already taking shape with the Simons Observatory. Currently under construction at the same high site in Chile, it is not a single telescope but a suite of them. This ambitious project will deploy several new instruments with even more sensitive detectors, capable of mapping the cosmic microwave background faster and with greater fidelity than ever before. Its primary goals are profound: to search for the elusive signature of primordial gravitational waves in the polarization of the ancient light, and to use the background radiation to weigh the ghostly neutrino particles that flooded the early universe. These telescopes are quiet sentinels in the desert, their polished mirrors and arrays of detectors pointed forever outward, listening for echoes. For the even older 21-centimeter signal from the cosmic dawn and dark ages, the technology shifts to a different kind of instrument, the massive radio telescope array. Projects like the Hydrogen Epoch of Reionization Array and the future Square Kilometre Array use hundreds or even thousands of simple radio antennas spread over vast distances. They work not as a single giant dish, but as a synchronized network, combining their signals to create a virtual telescope with a collecting area sometimes measured in square kilometers. They are often built in remote radio-quiet reserves, places shielded from the constant buzz of human civilization, cell phones, satellites, and television broadcasts. In these silent zones, they can tune to the specific low-frequency radio waves that correspond to the stretched signal of ancient hydrogen, hoping to pick its faint voice out of the cosmic static. Whether in the silent vacuum of space or the thin, dry air of a mountaintop desert, these instruments share a common purpose. They are all exquisitely tuned to listen for light that has been traveling for most of cosmic history. By choosing the right wavelength and eliminating earthly interference, they give us the clearest possible window into epochs long gone, transforming theoretical whispers into precise, measurable data. Each observation is an act of chronological discovery, peeling back layers of time to reveal the universe's deepest origins. Our entire cosmic story is told from within a single vast sphere of light. This is the ultimate limit of our vision, a frontier called the particle horizon. It is not a physical wall or barrier in space, but a temporal one defined by the most fundamental rule in the cosmos: nothing can travel faster than light. Because the universe has a finite age, roughly 13.8 billion years, light from the most distant regions has only had that much time to journey toward us. Imagine standing in the center of a darkening forest holding a lantern. The light from your lantern only illuminates the trees within a certain radius. The trees farther out remain shrouded in darkness. You know the forest extends beyond that circle of light, but you cannot see it directly. Our position in the cosmos is precisely that. We are at the center of our observable universe, not because we are in a special location, but because observation is always centered on the observer. Every point in the cosmos has its own observable sphere, its own particle horizon. This creates a profound and humbling reality. The farthest light we can possibly see is the cosmic microwave background, the afterglow released when the universe became transparent. That light has been traveling toward us for almost the entire age of the cosmos. But here is where intuition bends. The distance to that source is not simply 13.8 billion light-years. While the light has traveled for that long, the space through which it journeyed has been stretching the entire time. The source of that ancient photon, the patch of plasma that released it, is now much, much farther away due to the relentless expansion of the universe. By the time that photon finally reaches our telescopes, the region it came from is estimated to be about 46.5 billion light-years away. That distance defines the radius of our observable universe, a sphere nearly 93 billion light-years across, containing perhaps 2 trillion galaxies, all we will ever know. Everything within that sphere, from the nearest star to the most distant quasar, is part of our past light cone, a cascade of signals from different eras, all arriving here and now. The cosmic microwave background forms the inner surface of this sphere, the oldest wall of light. Anything that occurred before that moment of recombination, such as the inflationary epoch or the precise instant of the Big Bang, is hidden behind this glowing curtain. We infer those earlier events from the patterns imprinted on the curtain, like detectives studying the outside of a sealed room by the shadows cast on its windows. Furthermore, any event or object beyond our particle horizon, no matter how grand, is forever outside our causal reach. Its light has not had time to reach us, and it never will if cosmic expansion continues to accelerate. We are separated by an ever-widening gulf of space that expands faster than light can cross it. This horizon frames every discovery we have discussed. When we study the detailed map of the cosmic microwave background, we are not looking at the entire newborn universe, we are looking at the entire newborn universe that is visible to us. Our cosmic vista, for all its grandeur, is a local history. It is the story of our patch, the volume of space from which information can have reached us. There are undoubtedly other patches, other horizons centered on galaxies in the unimaginable distance containing their own histories, and perhaps their own versions of this same ancient light. We are in a very real sense isolated within our sphere of time. This limitation is not a failure of our technology, but a fundamental consequence of living in a universe with a beginning and a finite speed for information. It means our knowledge of the cosmos, no matter how deep, will always be a story told from a single point of view, a magnificent but partial autobiography of the visible universe. And so we are left to wonder if the light we can see tells such a rich story, what unimaginable chapters lie forever in the dark beyond our horizon. Light may be our most faithful messenger, but it is not the only one. To peer even closer to the moment of creation, we must learn to listen for signals that are not light at all. Two of the most profound possibilities are ghostly particles and ripples in space itself, each carrying a story from a time before the first atoms ever formed. First, consider a sea of ghosts, roughly 1 second after the beginning, when the universe was still a seething soup of particles. A crucial transition occurred. The cosmos had cooled enough for neutrinos, those famously elusive subatomic particles, to stop interacting frequently with the rest of the matter and radiation. They decoupled, streaming free to travel across the universe virtually untouched. This created a cosmic neutrino background, a relic sea of these particles that should permeate all of space, even more ancient than the cosmic microwave background. Every cubic centimeter of space around you is theorized to contain about 300 of these primordial neutrinos from the Big Bang. They are a direct snapshot of the universe at 1 second old. Yet detecting them is a challenge of almost unimaginable difficulty. Neutrinos interact so weakly with normal matter that they pass through our entire planet as if it were empty space. The low energy of these ancient ones makes them even more ghostly. Our current technology simply cannot catch them. They represent a chapter of cosmic history we know must exist, written in a language we cannot yet read, a record waiting to be discovered. The second signal comes not from particles but from the fabric of reality. If the inflationary epoch happened, it should have been a tremendously energetic event, shaking the very foundations of space and time. These tremors would have generated primordial gravitational waves, ripples in the curvature of space itself that have been traveling through the cosmos ever since. Unlike the neutrinos, these waves have a potential signature we are actively hunting for. As they passed through the universe in those first moments, they would have subtly influenced the polarization of the cosmic microwave background, imprinting that unique, swirling B-mode pattern. Detecting that specific curl in the ancient light would be more than just evidence of gravitational waves. It would be a direct message from the inflationary epoch itself, a probe of the universe's condition in its first trillionth of a second. It would tell us about the incredible energy scales at play during that hyper-expansion, scales far beyond anything our particle colliders can ever recreate. Together, these potential signals represent the ultimate frontiers of early universe cosmology. The cosmic neutrino background offers a glimpse into a hot, dense universe just moments old. Primordial gravitational waves could carry the echo of its most dramatic growth spurt. They are complementary stories to the one told by light, each providing a different vantage point on creation. While the neutrino background remains a theoretical treasure just beyond our grasp, The hunt for its gravitational counterpart is one of the most compelling quests in modern science. Finding either would be like discovering a new, deeper layer to the universe's autobiography, a chapter written not in light but in the quietest tremors of matter and space. Our ability to witness this ancient light is itself a profound clue about the nature of reality. The universe we observe is not just any random cosmos, it is one that allows for observers to exist within it. This idea is known as the Anthropic Principle, a philosophical perspective that connects our quest for cosmic origins directly to our own existence. Think of it this way: the specific laws of physics, the precise strengths of forces, and the delicate initial conditions that led to a universe with stable atoms, long-lived stars, and planets like Earth are the very same conditions that produced a detectable cosmic microwave background. Had the universe expanded just a fraction faster, matter would have spread out too quickly for galaxies to ever form. Had the nuclear forces been slightly weaker, hydrogen would never fuse into helium and stars would never ignite. In such alternate realities, there would be no one to ask questions about the cosmos and no ancient light to observe in the first place. We find ourselves in a cosmic era that is a kind of Goldilocks window for observation. The afterglow of creation is still visible, having stretched into the microwave part of the spectrum. It is faint enough that it does not bathe planets in sterilizing radiation, yet still strong enough for our telescopes to capture its intricate details. This window is not permanent. In the far future, as expansion continues to accelerate, the cosmic microwave background will redshift into complete obscurity, and distant galaxies will vanish beyond the horizon. For a future civilization born billions of years from now, the universe would appear profoundly empty and dark, with no evidence of a hot, dense beginning. They would have no cosmic fossil to study. Our present moment is special, not in a geographical sense, but in a chronological one. We live at a time when the universe is both old enough to have built complex structures like ourselves, and young enough that its fiery birth still leaves a visible echo in our skies. This perspective reframes our entire journey of discovery. The ancient light we trace is more than a relic. It is a signature of a universe finely tuned to allow for the emergence of consciousness capable of wondering about it. Our investigation into the first photons is therefore a deeply self-reflective act. We are not just studying the distant past, we are uncovering the necessary preconditions for our own story. The constants etched into that baby picture of the cosmos are the same constants that govern the chemistry of life. In decoding the universe's earliest signals, we are, in a very real sense, reading the instructions that made our own existence possible. This connection turns cosmology from a purely external science into a personal exploration, asking not only where we came from, but why we are here to ask the question at all. The connection between that ancient blueprint and our modern cosmos is a triumph of cosmic archaeology. We possess two extraordinary artifacts, one from the very beginning and one from the present day. The first is the detailed map of the cosmic microwave background, a fossilized imprint of the universe at 380,000 years old. The second is the immense, three-dimensional chart of the nearby universe, painstakingly assembled by sky surveys that have mapped the positions of millions of galaxies. The true test of our story is whether these two artifacts, separated by nearly the entire age of time, tell the same story. They do, with breathtaking precision. Those subtle hot and cold spots on that early picture are not random. They have a specific statistical signature, a predictable pattern of how common different-sized ripples are. Cosmologists can take that pattern from the infant universe and run it forward through the known laws of physics, primarily the relentless force of gravity acting over 13.8 billion years. Their supercomputer simulations show a clear prediction. Gravity should amplify those tiny overdensities, pulling in dark matter and gas to form a vast, interconnected network of filaments and voids, a cosmic web. When we compare this prediction to the actual maps of galaxy surveys like the Sloan Digital Sky Survey, the match is unmistakable. The galaxies we see today are not scattered randomly. They trace out that exact web-like structure, clustering along filaments and gathering at dense nodes, just as the ancient seeds suggested they would. It is as if we had the blueprint for a grand cathedral and then, billions of years later, walked into the finished building to find every arch and column exactly where the plans said they would be. This alignment is a powerful validation of our entire cosmological model. It confirms that the simple ingredients we read from the cosmic microwave background, ordinary matter, dark matter, and dark energy, are sufficient to build the universe we see around us. The process is a slow cosmic domino effect, a region that was a fraction of a percent denser than its surroundings in the early universe attracted slightly more matter. This made it even denser, attracting even more in a self-reinforcing cycle that spanned eons. What began as a microscopic quantum fluctuation imprinted on the ancient light grew into a giant cluster of galaxies, each containing hundreds of billions of stars. Every magnificent spiral galaxy, every distant quasar, exists because of a specific whisper in the cosmic background radiation. This deep consistency check is why scientists speak with such confidence about our cosmic history. We are not just interpreting a single, ancient clue. We have connected it directly to the present, closing the loop of causality across nearly 14 billion years. The universe we observe today is the mature, evolved form of the infant we see in that first light, and the family resemblance is undeniable. Yet that magnificent map of the beginning holds strange whispers that do not quite fit the story. Despite its profound agreement with our cosmic model, the detailed portrait of the cosmic microwave background contains a few curious and persistent features that cosmologists refer to as anomalies. These are oddities in the data, subtle patterns that seem to defy the expectations of a universe that is statistically uniform and without a preferred direction. They are the faint, unresolved notes in an otherwise harmonious symphony. One of the most famous is known simply as the cold spot. In an otherwise mottled sky, this is an unusually large and pronounced region of cooler temperature spanning a vast area. If it were merely a random statistical fluctuation, it would be an exceptionally rare one, like rolling a dice and getting the same number a dozen times in a row. Some explanations suggest it might be a foreground effect, perhaps a gigantic and nearly empty supervoid between us and the ancient light, a cosmic tunnel that subtly dims the background radiation. Others propose more exotic ideas, like a collision with another universe during the Inflationary Epoch, a speculative concept that captures the imagination. While the supervoid explanation is currently favored, the cold spot remains an active puzzle, a reminder that our maps may still contain uncharted territories. Another set of anomalies concerns alignment. According to the standard model, the hot and cold spots in the cosmic microwave background should be randomly oriented, with no large-scale directionality. Yet some analyses suggest a surprising degree of alignment across the largest scales, a pattern some researchers have informally noted. This apparent correlation, if real, would hint at a preferred direction in the cosmos, a fundamental break from the principle that the universe looks the same in all directions. It is as if the universe's earliest portrait had a faint, subtle mark upon it. The scientific community approaches these features with a disciplined blend of curiosity and caution. The first and most critical step is to rule out more mundane causes. Could instrumental noise or subtle errors in data processing create such patterns? Could they be the imprint of our own solar system's motion through the cosmic background, or the glow of dust within our Milky Way galaxy? Exhaustive checks are performed, and while many anomalies diminish under scrutiny, a few stubbornly persist. This careful process ensures that the pursuit of new physics is grounded in rigorous observation, not in the seductive pull of a statistical fluke. ultimately, these mysteries serve a vital purpose. They are the questions that prevent cosmology from becoming a closed book. They drive the design of the next generation of observatories, like the Simon's Observatory, which will measure the ancient light with even greater precision to see if these oddities are mere mirages or genuine insights into our foundational model. They remind us that the universe's first light, for all we have learned from it, may still hold surprises about the true nature of reality. In the quiet anomalies of the map, we find the motivation to look deeper, to listen more carefully, and to remain humble before the story the cosmos is still telling. The anomalies in our cosmic map are not dead ends. They are signposts pointing toward the next great leap in understanding. To follow them, we are building a new generation of eyes and ears, instruments of such staggering sensitivity, they will listen to the dawn of time with a clarity we can now only dream of. The future of early universe cosmology is being written in the designs of missions that will push our perception to its absolute limits. In space, the European Space Agency is studying a visionary concept called the Cosmic Origins Explorer, or CORE. This proposed satellite would be a direct successor to the legendary Planck mission, but with a singular, profound focus to map the polarization of the cosmic microwave background with a precision 10 times greater. Its suite of ultra-sensitive detectors, cooled to near absolute zero, would scan the entire sky, hunting for the faint, curling signature of primordial gravitational waves, those elusive B modes. Finding them would be a discovery on par with the original detection of the background radiation itself, offering a direct glimpse into the physics of inflation. Even if the primordial B modes remain hidden, the exquisite data from CORE would measure the other properties of the ancient light with such fidelity that we could weigh the neutrino, test the nature of dark matter, and probe the fundamental symmetries of the universe moments after it began. On the ground, an even more colossal effort is taking shape, known as CMB Stage 4. This is not a single telescope, but a coordinated army of them. Imagine multiple new instruments deployed to the high, dry deserts of Chile and the frigid, stable air of the South Pole, all working in concert. CMB Stage 4 aims to survey the sky with an array of over 500,000 detectors, creating a map of the cosmic microwave background that is exponentially more detailed than anything before it. Its goal is to achieve a definitive measurement, either confirming the existence of primordial gravitational waves or ruling out entire classes of inflationary models. It represents a monumental collaboration, a global endeavor to answer the universe's first questions by listening more intently than ever to its oldest song. Our quest to witness the cosmic dawn when the first stars ignited is also entering a transformative phase. While the square kilometer array prepares to map the 21-centimeter signal in detail, other pioneering projects are already attempting to hear its very first note. Experiments like the hydrogen epoch of reionization array and the upcoming packed ultra-wide band mapping array are radio telescopes of a novel design. They use vast fields of simple dipole antennas spread across remote, radio-quiet landscapes to capture the ultra-low frequency waves emitted by the neutral hydrogen of the early universe. Their challenge is immense as they must filter out the roaring static of our own galaxy and Earth-based interference, a task akin to hearing a pin drop in a hurricane. But success would give us something revolutionary, a three-dimensional movie of the universe's adolescence, frame by frame, as the first structures flickered to life and began to sculpt the cosmos. These future endeavors are more than just bigger telescopes. They are machines for asking deeper questions. They promise to sharpen the baby picture of our universe into a high-definition portrait, one that may reveal wrinkles and features we have not yet even imagined. They could uncover new physics operating at energies forever beyond the reach of any particle collider, written into the fabric of the ancient sky. With each incremental increase in sensitivity, we open a new channel to the past, to tuning into frequencies of reality that have been silent since the beginning. What we hear next may not just refine our story, but could very well tell us an entirely new one. This digital bridge between past and present is built inside the world's most powerful supercomputers. Since we cannot rewind the cosmos and watch it form, we have learned to grow our own. Cosmological simulations are vast, intricate experiments conducted in a virtual laboratory, where scientists start with the universe's initial conditions, the precise fluctuations encoded in the cosmic microwave background, and then set the laws of physics in motion. They feed the computer a recipe based on our best models, a mix of dark matter, ordinary matter, dark energy, and the fundamental forces, and then press play on 13.8 billion years of cosmic history. What unfolds is a breathtaking dance of creation rendered in exquisite detail. These are not simple animations, they are rigorous numerical experiments. The virtual universe begins as a nearly smooth grid of points, each representing a parcel of dark matter and gas, seeded with the exact pattern of density variations we see in the ancient light. Then gravity takes over. The code calculates the pull between every single parcel, a task of staggering complexity that requires machines capable of performing quadrillions of calculations per second. Over millions of simulated years, the subtle overdensities begin to attract more matter, growing into halos of dark matter. Gas, following the gravitational blueprint of this invisible scaffolding, flows into these halos, cools, and begins to swirl. When conditions are right, the simulation triggers the birth of virtual stars, whose fierce radiation and eventual supernova explosions blast material back out into space, enriching it with heavy elements and regulating the growth of future generations. This cycle of creation and feedback is programmed in, allowing the virtual cosmos to self-organize from the bottom up. The true power of these simulations lies in comparison. Once a simulated universe has fully evolved, scientists can analyze it just as they do the real one. They can create mock observations, generating synthetic maps of galaxy distributions, measuring the clustering of matter, and even simulating the faint glow of the intergalactic medium. They then hold these digital snapshots up against actual data from telescopes like the Hubble or the Sloan Digital Sky Survey. Do the virtual galaxies cluster in the same intricate web as real ones? Do they have the right mix of shapes, sizes, and ages? This process acts as a rigorous test for our theories. If a simulation based on a particular model of dark matter or star formation produces a universe that looks nothing like our own, that model is likely wrong. It is a process of cosmic trial and error refined in silicon. These digital universes have become indispensable guides. They help us interpret what we see in the real sky, revealing how the invisible hand of dark matter shapes the luminous galaxies we observe. They allow us to revisit dynamic events like galaxy interactions to understand their history. Most importantly, they bridge the immense gap between the smooth simplicity of the cosmic microwave background and the breathtaking complexity of the present-day cosmos, showing step by step how one gave rise to the other. In these vast digital realms, we do not just observe the story of the universe, we actively participate in its telling, testing our understanding against a reality we are striving to recreate. The universe's oldest light is not locked away in a vault for scientists alone. It belongs to everyone. In a remarkable act of scientific openness, the teams behind missions like Planck and the Wilkinson Microwave Anisotropy Probe have released their full sky maps to the public. This treasure trove of data, the detailed portrait of the infant cosmos, is available for download by anyone with an internet connection and a sense of curiosity. You can find these immense data sets on the official websites of NASA and the European Space Agency, where they are archived and freely accessible. It is a profound form of democratization, turning the most fundamental questions about our origins into a shared human exploration. What can you actually do with this data? The possibilities are surprisingly tangible. With some basic software skills, you can load these all sky maps and visualize them yourself. You can manipulate the contrast to highlight the subtle temperature differences, those ancient wrinkles that seeded all of structure. You can zoom in on the famous cold spot or trace the patterns of the acoustic oscillations. For students and educators, this is an incredible resource. It allows for real hands-on engagement with the same information professional cosmologists use to understand the composition of the universe. It transforms abstract concepts into something you can see and interact with directly on your screen. Beyond simple visualization, there are platforms designed to bring this data to life for the public. Projects like the World-Wide Telescope, developed by Microsoft and now managed by the American Astronomical Society, allow you to take a seamless tour of the cosmos. You can journey from the planets in our solar system all the way out to the cosmic microwave background. This places that ancient glow in its proper context as the most distant visible layer of our universe. Other online tools let you overlay different frequencies of light, showing how scientists separate the pristine cosmic signal from the foreground fog of our own galaxy. The engagement goes even further into the realm of citizen science. While the meticulous analysis of the cosmic microwave background requires advanced expertise, new telescopes gathering data on the universe's later chapters often welcome help from the public. Platforms like Zooniverse host projects where volunteers can assist researchers by classifying images of galaxies. This helps to map the large-scale structure that grew from those primordial seeds. By participating, you are not just learning about the cosmic web, you are actively helping to chart it. This collective effort accelerates discovery and creates a powerful bridge between the public and the frontiers of research. This open access philosophy does more than just share information. It builds a deeper, more personal connection to the cosmos. When you can pull up the universe's earliest portrait on your own computer, a fundamental shift occurs. These are not just facts in a textbook, they are discoveries you can explore in a digital sense. It makes the grandeur of cosmology feel immediate and participatory. For a student wondering about a career in science, or simply for anyone who has ever looked up at the night sky with wonder, this access can be the spark that ignites a lifelong passion. It reinforces a beautiful idea that the story of where we came from is not owned by any institution, but is a narrative we are all invited to read and perhaps to help write. The ancient light we can measure tells a story with a distinct and startling opening chapter. For millennia, human cultures have pondered whether the cosmos had a beginning or has simply existed forever in some form. The cosmic microwave background provides our strongest empirical answer. That pervasive, cooled glow is not consistent with a static, eternal universe. It is the fading ember of a singular, hot, and dense origin, the Big Bang. This evidence powerfully supports the idea that time itself, as we understand it, had a definite starting point nearly 14 billion years ago. While we cannot peer behind the curtain of that first fiery moment, the existence of this relic fundamentally challenges models of an eternal, cyclical cosmos without change. It suggests our entire reality, all of space and time, emerged from a state beyond our current physical description. This leads to a second, equally staggering implication about scale. The part of the universe we can see, defined by the light that has reached us, is immense but finite. Yet the remarkable uniformity of the cosmic microwave background, its consistency in all directions, hints at a reality far grander. Inflationary theory suggests the observable cosmos is just a tiny bubble within a vastly larger, and perhaps infinite, expanse. The conditions we see were stretched smooth across our entire horizon, but what lies beyond that horizon is, by definition, unknowable. We are left with the humbling realization that everything we study, every galaxy in our deepest surveys, may be but a single island in an endless cosmic archipelago. The universe is likely much, much bigger than we can ever see. Contemplating these photons from the dawn of time inevitably brings us to thoughts of destiny. The same data that reveals the beginning also charts the future. The precise composition read from the ancient light, dominated by dark energy, points toward a specific fate, a gradual fading rather than a fiery collapse. As expansion accelerates, distant galaxies will vanish from view, the cosmic background radiation will redshift into silence, and the universe will grow cold, dark, and isolated. Our current epoch, where the past is still visible and the cosmos is rich with structure, is a transient golden age for observation. We exist in a privileged moment in cosmic history, able to look back and see the evidence of our own origins. This knowledge fosters a profound sense of cosmic humility. Our entire recorded history is less than a blink in the lifetime of the universe. Our planet is a speck orbiting an ordinary star in the suburbs of a common galaxy. Yet, we are made of atoms forged in those first stars, and we have evolved the consciousness to decode the light from creation itself. In a cosmos that shows no obvious purpose or design, we find ourselves as the part of the universe that has become self-aware, capable of wonder and inquiry. The ancient light connects our brief, personal story directly to the grandest narrative of all, offering not a promise of centrality, but a gift of connection. It tells us that we are not just in the universe, we are a product of it, and in our quest to understand these first signals, the universe is, in a very real sense, beginning to understand itself. The universe's true beginning is often lost in translation. One of the most persistent myths is that the Big Bang was an explosion that happened at a single point in an empty void. This mental picture feels intuitive, but it is fundamentally incorrect. The Big Bang was not an explosion into space, it was the rapid expansion of space itself. There was no pre-existing emptiness for the universe to expand into. Instead, every point in the cosmos, every location we can now observe, was once incredibly close together. The expansion is not like debris flying outward from a central blast, but more like the stretching of the surface of a balloon as it inflates. If you mark two dots on a deflated balloon, they move apart as you blow it up, not because the dots are traveling across the surface, but because the fabric between them is stretching. This is why we see galaxies receding from us in all directions, and why every observer, no matter where they are, would see the same thing. The universe has no center because the expansion happened everywhere at once. This directly leads to another common misunderstanding about the cosmic microwave background. When we say it is the oldest light we can see, it is easy to imagine we are looking out to the edge of a cosmic sphere, seeing the boundary where the universe ends. That is not what we are seeing. The CMB is not a wall at the edge of creation. It is a surface of last scattering that surrounds us in every direction. Because light takes time to travel, looking out into space is always looking back in time. When we point our telescopes in any direction and detect the microwave background, we are seeing the hot plasma from a time when the universe was only 380,000 years old. That plasma filled all of space. We are essentially looking back to a specific moment in time, not to a specific distant wall. It is like being in the middle of a dense fog that suddenly clears. The light from the moment the fog cleared reaches you from all around, creating a glowing shell. You are not at the center of the fog, you are simply at the center of your own observation of it. Another frequent idea is that the entire universe was once the size of a tiny subatomic particle. This is a simplification that can be misleading. The statement refers only to our observable universe, the portion of the cosmos from which light has had time to reach us. That region was indeed incredibly small and unfathomably dense. However, based on the evidence of its flat geometry and the theory of inflation, the universe as a whole was likely infinite even at that earliest moment. It is a difficult concept to grasp, but imagine an infinite sheet of rubber that is infinitely dense. Now imagine that sheet expanding everywhere at once. A finite patch of that sheet, which would become our observable universe, was compressed into a minuscule volume, but the infinite sheet itself always remained infinite. The Big Bang describes the hot, dense state of that entire infinite expanse, not the popping into existence of a finite cosmos from a single point. Correcting these myths is not just about scientific accuracy. It changes how we feel about our place in the cosmos. We are not in the aftermath of a cosmic explosion, drifting on a remnant piece of debris. We are part of a dynamic, stretching fabric that has been evolving from a state of incredible energy for nearly 14 billion years. The light we see is not from a distant edge, but from a moment when the entire cosmos was transformed. And the scale of it all suggests a reality whose true vastness may forever lie beyond our horizon, a humbling and awe-inspiring thought that makes the story told by the ancient light even more profound. The quest to hear the universe's first whispers required inventing new ways to listen, and those inventions now speak to us every day. The technology born from this cosmic detective work has quietly woven itself into the fabric of modern life, proving that the search for our deepest origins often illuminates our present world. Consider the quiet hum of a mobile phone call or the crisp image on a satellite television broadcast. The clarity of these everyday signals owes a debt to the silent depths of space. In their effort to detect the faintest radio whispers from distant galaxies and the cosmic microwave background, radio astronomers faced a fundamental problem: noise. Their instruments needed to amplify incredibly weak signals without adding their own disruptive static. This challenge drove the development of ultra-low noise amplifiers, devices that could boost a signal while introducing minimal electronic interference. The specialized transistors and circuit designs perfected for observatories became the foundation for the amplifiers in satellite communication receivers and cellular network base stations. The technology that lets us hear a voice from across the globe was first refined to listen for echoes from the dawn of time. The same principle of exquisite sensitivity extends to the detectors that map the cosmic microwave background itself. To perceive the subtle warmth of that ancient light, scientists had to build sensors of almost unimaginable precision and keep them colder than the void of space. This led to breakthroughs in cryogenics, the science of extreme cooling, and in the creation of superconducting materials that lose all electrical resistance at temperatures near absolute zero. These are not just laboratory curiosities. The same superconducting quantum interference devices developed for cosmology experiments are now used in highly sensitive medical scanners. They can detect the incredibly faint magnetic fields produced by brain activity, enabling magnetoencephalography to map neural function without any invasive procedure. The drive to see the universe's first light has given us new ways to see inside the human mind. Even the challenge of processing the data holds unexpected gifts. Mapping the cosmic microwave background involves sifting a pristine cosmic signal from a fog of foreground noise, a task of staggering computational complexity. The algorithms and statistical techniques created to clean these cosmic maps, to separate the faint pattern of primordial sound waves from the glare of the Milky Way, have found powerful applications in other fields. They inform how we process medical scans to find subtle signs of illness, how we analyze financial markets for underlying patterns, and how we teach machines to recognize images and speech. The problem of finding order in cosmic chaos has advanced the very tools we use to find meaning in vast streams of information. This flow of knowledge is a beautiful reminder that fundamental curiosity and practical innovation are not separate paths, but part of the same journey. We look to the farthest horizon to understand our place in the cosmos, and in doing so, we often discover new ways to connect, to heal, and to understand our own world. The story of the first light is not locked in the past. It is actively being written into the technology that shapes our future. But what if the beginning was not the beginning? While the cosmic microwave background marks the edge of our observational horizon, the human mind naturally pushes further, asking what came before. Some of the most daring theories in modern cosmology propose that our Big Bang was not a singular creation event, but a transition, a rebirth from a prior state of existence. These are the models of a cyclic or bouncing universe, where the cosmos undergoes endless cycles of expansion, contraction, and renewal. In this breathtaking vision, the universe has no ultimate start or finish, only an eternal rhythm of cosmic seasons. The central idea is both ancient and revolutionary. Imagine the universe not as a one-time explosion, but as a great cosmic lung, breathing in and out over scales of time that dwarf our imagination. In one version, driven by the mysterious properties of dark energy and string theory, our current phase of accelerated expansion does not lead to a cold, eternal fade. Instead, it sets the stage for a great reversal. After trillions of years, expansion could slow, reverse, and the entire cosmos would begin to contract. Galaxies would draw closer, the temperature would rise, and all matter and energy would be compressed into an incredibly hot, dense state. But instead of collapsing into a singularity and ending, this bounce phase proposes a quantum repulsion, a cosmic springboard that triggers a new expansion, a new Big Bang. Our entire observable universe, with its galaxies and microwave background, would then be just one chapter in an infinite series. This raises a tantalizing possibility. If our universe emerged from a previous one, might there be faint scars or memories carried over? Could the cosmic microwave background, our oldest fossil, contain subtle imprints from the cycle that came before ours? Theorists suggest that if the bounce was not perfectly smooth, if it involved chaotic dynamics or collisions between higher dimensional structures called branes in string theory, it could have left specific patterns in the distribution of the hot and cold spots. These might appear as unusual alignments on the largest scales, or a specific type of signal in the polarization that our current telescopes have not yet been sensitive enough to detect. Finding such a pattern would be like discovering a watermark on the universe's birth certificate, a sign that this document has been issued before. These ideas exist at the very frontier of physics, where general relativity meets the strange rules of quantum mechanics. They require us to think about what happens to space and time themselves under conditions of infinite density, a realm where our current laws break down. While compelling, they remain highly speculative, lacking the concrete observational evidence that supports the standard Big Bang model. They are not yet established science, but rather profound thought experiments that stretch our understanding of reality to its limits. They challenge the very meaning of first light. Is the cosmic microwave background the first light of all existence, or is it merely the oldest light from our current cosmic spring, following an unimaginably long winter of contraction? For now, the question remains open, a beautiful mystery that drives our most ambitious theoretical work and our most sensitive observations, as we listen to the ancient sky, wondering if it holds echoes of a time before time. That ancient light is a map of invisible forces. To read the story of the cosmic dawn, we must account for the universe's unseen architects, dark matter and dark energy. Their signatures are woven into the very fabric of the cosmic microwave background, influencing how those first signals formed and how they reach us today. Dark matter, which does not emit, absorb, or reflect light, played the crucial role of gravitational scaffolding. In the early universe, ordinary matter, the protons and electrons that make up atoms, was tightly coupled to intense radiation. This radiation pressure acted like a powerful wind, preventing atoms from clumping together easily. Dark matter, unaffected by this light, could begin to collapse under its own gravity much earlier. It formed vast, invisible wells, gravitational pits that ordinary matter would later flow into. The pattern of hot and cold spots we see in the cosmic microwave background is not just a map of where matter was, but a precise record of how gravity, dominated by dark matter, was already pulling the universe into shape. The specific statistical distribution of those spots, their sizes, and how common they are, is a direct fingerprint of how much dark matter existed. By analyzing this pattern, cosmologists determined that dark matter makes up about 27% of the universe's total content, the silent framework upon which all luminous structure was built. Dark energy writes its chapter later in the story, but its influence is retroactive, shaping how we interpret the ancient light's journey. This mysterious force, driving the accelerated expansion of the universe, affects the geometry of space itself. The cosmic microwave background acts as a cosmic yardstick. We know the physical size of the sound waves frozen into that light. By measuring their apparent angular size on the sky, we can deduce the geometry of the universe over the vast distance the light has traveled. The fact that these spots appear at a specific scale tells us the universe is geometrically flat. This flatness is a critical clue, tightly linked to the total density of the cosmos, which includes the contribution of dark energy. Furthermore, dark energy's accelerating push affects how far away the source of that ancient light actually is today. It stretches the path the photons traveled, changing our calculation of the distance to the last scattering surface. When we use the cosmic microwave background to measure the universe's expansion history, we see a clear signature, a shift that tells us dark energy began to dominate about 5 billion years ago, causing the growth of structure to slow even as the cosmos sped apart. Ultimately, the cosmic microwave background is our most precise ledger for the universe's budget. It is how we audited the cosmos and discovered its shocking composition, roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. We did not find dark matter and dark energy first and then look for their imprint in the ancient light. Instead, it was the exquisite details of that light, its fluctuations and geometry, that forced us to infer their existence. Every new, more sensitive map of this radiation is a sharper tool for probing these mysteries, constraining what dark matter could be made of and how the strength of dark energy might change over time. In this way, the oldest light we can see has become our primary guide to understanding the universe's most profound and hidden secrets. The entire cosmic story is a single, unbroken timeline written in light. Let us visualize this journey from the first fleeting moment to the present day to see how every chapter connects. Our story begins not with light, but with its absence in the unimaginably brief Planck epoch, the first 10 to the minus 43 seconds. Here, the four fundamental forces are unified and our current laws of physics break down. It is a realm of pure quantum potential, a seething foam where space and time themselves are not yet stable concepts. From this unfathomable state, the universe undergoes its dramatic inflationary expansion, stretching a subatomic volume to cosmic size in a fraction of a second and planting the quantum seeds of all future structure. As inflation ends, the universe is filled with a seething, opaque plasma of incredible energy. This is the primordial fireball where photons are born but instantly trapped. For nearly 400,000 years, light is a prisoner, bouncing furiously between free electrons in a brilliant, blinding fog. This is the era of last scattering, where the universe is a glowing, impenetrable soup. Then the temperature falls to a few thousand degrees. In the event called recombination, electrons combine with protons to form the first stable hydrogen atoms. The prison bars vanish. In that instant, the universe becomes transparent, and the first true light is set free. This burst of liberated photons rushing outward in every direction is the cosmic microwave background. It is the oldest fossil, a baby picture of the cosmos at 380,000 years old, and it carries the blueprint of everything to come. With that flash, the cosmos enters the true dark ages. For millions of years, there are no new sources of light. The universe expands in silence and darkness, a vast sea of neutral hydrogen cooling under the fading echo of that first signal. Yet gravity is at work. Slowly, relentlessly, it amplifies the tiny imperfections in that ancient light, pulling dark matter and gas into the first gravitational wells. This silent era is the crucial bridge, the quiet preparation for a new dawn. That dawn arrives with the ignition of the first stars. In pockets of gathered gas, nuclear fusion sparks to life. The cosmic dawn breaks, and for the first time since the initial flash, new light pierces the cosmic dark. These first stars are behemoths, blazing with fierce ultraviolet radiation that begins to carve bubbles in the neutral hydrogen, reionizing the universe in an epoch that lasts hundreds of millions of years. Their light is the sculptor of the modern cosmos. From these first stellar nurseries, gravity's work accelerates. Stars group into the first proto-galaxies, which merge and grow, spinning into majestic spirals and elliptical giants. Clusters of galaxies form, connected by vast filaments of dark matter in a great cosmic web. Within galaxies, generations of stars are born, live, and complete their cycles in tremendous explosions, forging heavy elements like carbon, oxygen, and iron. These elements are scattered into space, eventually coalescing into new stars, planets, and, on at least one world, life capable of looking up and wondering. The light from all these chapters is still traveling. The photon from a distant galaxy that strikes our telescope tonight began its journey billions of years ago. It shows us that galaxy not as it is, but as it was when the universe was young. The light from the cosmic microwave background is older still, a whisper from the very first page. When we point our instruments at the sky, we are not looking at separate objects in isolation. We are reading a continuous historical narrative. The quasar, the spiral galaxy, the faint glow of the microwave background, they are all different paragraphs in the same cosmic autobiography, each arriving from a different moment in time. This timeline reveals a profound unity. The light we capture today, whether from the Andromeda galaxy or the primordial plasma, is part of a single, coherent story of evolution. The earliest signals provide the foundational chapter, the initial conditions of density and geometry from which every subsequent structure unfurled. We are not just observers of disconnected phenomena, we are witnesses to a continuous thread of cosmic evolution, a story 13.8 billion years long, told in the language of photons finally reaching our eyes. Our journey through the whispers of creation ends with a simple, staggering truth. We are the universe looking back at itself. The atoms that form your hands, your eyes, even the thoughts reading these words, were forged in the hearts of stars that did not exist for billions of years after the Big Bang. And those stars themselves were born from the gentle gravitational pull of regions in the cosmos that were only a fraction of a percent denser than their surroundings. Those regions, those first seeds of everything, are the faint hot and cold spots we see mapped across the cosmic microwave background. We are, in the most literal sense, stardust that grew from the subtle ripples in the universe's oldest light. That primordial glow is far more than a cosmic fossil or a scientific dataset. It is our direct, tangible connection to the moment of creation, a story of origin written not in stone or myth, but in the quiet language of microwaves that we have, against all odds, learned to read. This entire epic of understanding unfolded from a single, persistent hum. The accidental discovery by Penzias and Wilson at Bell Labs opened a door we did not know existed. From that first detection of cosmic static, we built satellites to map its wrinkles, designed telescopes to listen for its polarized secrets, and constructed supercomputers to simulate the growth of galaxies from its blueprint. Each step reshaped our understanding of reality, revealing a cosmos dominated by mysterious dark matter and driven apart by an even more enigmatic dark energy. We moved from seeing a universe of stars and galaxies to comprehending a dynamic, evolving entity with a clear history and a measurable destiny. The quest is far from over. The next generation of observatories, from the ground-based arrays of the Simons Observatory to the visionary concepts for space-based telescopes, will listen with even greater sensitivity. They will hunt for the tremors of inflation in the light's polarization and try to hear the faint radio murmur of the universe's first stars. Each new instrument is a deeper probe into the unknown, asking questions we have only just begun to formulate. So the next time you step outside and feel the warmth of sunlight on your skin, pause for a moment. That light which powers our world and makes life possible is a direct descendant. It is the latest chapter in a lineage that stretches back in an unbroken chain to that first, universe-defining flash, when light was finally set free to travel across the ages. We are living in the glow of that ancient dawn, and we carry its story within us. If this voyage from the quantum seeds of reality to the conscious minds contemplating it has sparked your curiosity, we would love to hear your reflections. Share your thoughts in the comments below, and subscribe to join us as we continue exploring the profound and beautiful